Okay. Hello, everyone. Today's lecture, of course, is on double counting. Uh, so double counting, of course, like counting in two ways, all are very synonymous. The broad idea is you have some set S1, some set S2, and then you show that there is a bijection between them, or maybe sometimes it's obvious. And then you go ahead and conclude that they have the same cardinality. And of course, you see this in various ways. Some places you might see it is when you swap the order of two summations. Essentially, it's the same story everywhere. You're just looking at a particular object and then counting it in two different ways. Okay, so to get you all hyped about double counting, I'm going to do an interesting exercise that will prove, well, an interesting identity, and it will also be through double counting. Okay, so it's going to be a little interactive. Let's try to do that. Okay, so let's imagine that you're the security. There's a big party going on in this circle right here, and you see this opening there. Like you're the security for the party, and you have to let three people in, like up to three people in, and you have three passes with you. So the first pass is like a special pass, right? And then you have two normal passes. So you have normal pass one, and then you have normal pass two. Well, some of you might have actually seen this before. If you have, then just let the magic happen. If you all haven't, then it's pretty good because then you all see it for the first time. Okay, so there's three kinds of passes. One is a special pass, and then there's a normal pass one, and then there's normal pass two. So here, note that I've numbered them because I do want to specify that they are distinct passes, so they're not interchangeable. Okay, so there are n plus one people outside, right? They want to get into the party. You have to choose up to three of them. And the way you do it is as follows. You can first, so the conditions are, let's say you give the special pass.
What is pass?
So in that case, A should be bigger than B and C, right? And those are the only conditions. So that's the only condition that you have. A should be bigger than B and C. Here, note that B could be equal to C. That's an important thing to note. Like B is allowed to be equal to C. So you could give the two normal passes to the same person. And what you need to do is find all the arrangements, the number of possible ways you could distribute these passes. The pass is just like a ticket. It doesn't really matter. All you're doing is assigning each of these fields some value A, B, or C. And then you're trying to ensure this condition. Okay, so how many ways are there to do this? Okay, so there are two ways you might go about this. So the first is to actually fix the special person, right? So let's say the special person is A. So then you have A and you've given the special pass to person A. And now B and C have to be assigned among 1 to A minus 1, right? How many ways are there to do that?
A minus 1, C2?
No, that's incorrect because I said that they're allowed, they could be same, they could be the same. So you could give the two passes to the same person, and also the passes are like distinguishable. Yes, exactly. A minus 1 whole squared, right? And so if you just iterate over what are like the possibility for, the person who gets the special pass, in that case, you'll just get an answer of sum of I squared, right? This is what you get on the one hand. So of course, now a lot of you would know what this evaluates out to is a polynomial in n, but let's try to arrive at that polynomial in a different way and thus display the power of double counting, so to say. Okay, so now you're choosing three people, right? So there are fundamentally two possibilities. The first possibility is that you pick three distinct people, right? And the second possibility is that you pick two distinct people, in which case both the normal passes go to the same individual, right?
Yeah.
Okay,
Also,
so
I
how many
think
ways are there to choose?
the summation,
sorry?
it will go from 1 to n minus 1 because that's A minus
No, I already
Again,
had
okay.
n plus 1 people with it, so
Yeah.
that problem is fixed. Okay, so one possibility is you choose three distinct people. If I choose three distinct people, then the person who gets the special pass is uniquely determined, right? Because of course, if you have three individuals,
Yeah.
only the oldest could, sorry, only
Yes.
the latest could get the special pass. And so, how many ways are there to choose three distinct people?
N plus 1 choose.
N plus one choose three, right? So, so on the one hand, my count is equal to this, and on the other hand, let's now count that. So, on the other hand, it's just all the cases that one could have, and then all the cases two could have. You're just going to sum those up. So, the number of possibilities for one is n plus one choose three, because any three distinct people you pick, the oldest, let's assume this is their ages or something. So the oldest would get one, sorry, oldest would get the special pass, and the other two would get normal passes. But how many ways are there to choose who gets the normal pass one and normal pass two?
2.
There are two ways, right? So we need to multiply two here because so you have, let's say you select I, J, K, I less than J less than K. These are distinct people. So K must be the person who gets the special pass. And now normal pass one and normal pass two, you can decide between I and J. So it could be I gets pass one and J gets pass two, or the other way around. So you have two times n plus one choose three ways from case one. The other case is that you have two distinct people. In that case, you of course have, again, so you have, let's say A and B, or I and J, let's keep systematic nomenclature. So if you have I less than J, then of course, again, we see that J must get the special pass, right? Because J has higher priority. And then you have I. I actually must receive both the normal passes now because it's only two distinct people who get any passes at all, right? And so what's the total number of ways to for case two to happen?
N
We have
plus
to
1 choose 2.
subtract the case when I equals to 0.
Sorry.
We have to subtract the number of cases when I equals to 0. Because
No, we don't have to go with those, right? Because only three, like you can only have three people or two people. Okay, so you have I less than J here. And how many ways are there to choose two distinct people?
N plus 1.
N plus one choose two, right? So you just choose these two people, and then the one with the lower number will get both tickets, whereas J gets the special pass or pass tickets interchangeable, let's assume. Okay, and now this is polynomial n, and if you work it out, it actually comes out to be this. So this offers an alternate proof for this very famous identity. One thing which you might note is that this actually works for bigger exponents as well, but maybe not too big. Maybe 10 would probably not be feasible. But certainly for 3 and 4, you can experiment with this and try to just rerun the argument in the same way we have here. So, and then the way you do it, of course, is by increasing the number of normal passes. So in I cube, for example, you'd have 3 normal passes. So, okay, so by just counting some object in two ways, we were able to actually prove an algebraic identity. That is not the main purpose of what we're going to discuss or the main theme of the problems anyway, but it just shows how powerful double counting can be, right? Because, yeah. Okay, so is everybody clear with this? Then in that case, we can just move on.
Yeah.
Okay. So, of course, double counting is perhaps best understood through problems. So we'll discuss some problems first. Okay. Um, right, let me just attach it. I hope everyone can see that problem. I'll just paste it. Right. So the problem says that you have these positive integers, a1 to an, and they're all among the first m positive integers. And bk is defined as the number of ai for which ai is at least k. And you have to show that this is true. So of course, given the lecture's name, you know that this is some double counting. But of course, the most important thing to figure out in any problem that you're trying to use double counting on is what are you counting? That's perhaps the first step, right? And then you can try to find multiple ways in which you could count it. So what should be the object to counting? So actually, there is a nice pictorial. We have seen this fact, which we'll discuss once we're done with the uh, double counting proof. Does anyone have any ideas?
Like the number of times AI appears in the BIs.
Okay, that's a bit vague, but sounds promising. Yeah, Athar, go on.
If we do something like pairs of integers n and ai such that ai is greater than or equal to n, because like if we fix n and then vary ai, we get the RHS, and we fix ai and then vary n, we get the LHS.
I'm
number
not
of
sure
pairs.
I
So what I'm saying is like
understand.
pairs of integers, let's say integer k, and one of the ai's such that
Right.
k is less than or equal to ai.
Right. Yes.
That's the
Yes, this is
pair.
exactly it.
That's also
Right. Exactly. So the idea is to count the pairs in I comma L in this set such that AI is at least L. This is the object that we're counting. We're counting these pairs, the set of these pairs, we're trying to count them. Right? And on the one hand, if we do this by I, so let's say we fix some I, how many L are there such that AI is at least L? How many positive integers L like that? There's AI of them, right? There's AI positive integers at most AI. And so on the one hand, this is just sum of AI. And this is your count, let's say. And now we're going to count it by L. So by L, how many AI are there such that AI is at least L? Well, that's exactly BL, right? And so this is just this. And so you prove this. Is that clear to everyone? Right.
Sorry,
So
but
now let's actually.
1 second. How do you count it the first way?
The first way is by fixing I. So you fix the index I that you choose. So now AI is fixed, and you're just trying to count the number of positive integers L among the first M, which are at most AI. Because AI is less than or equal to M, there's exactly AI of these. Something like you have AI, then M, and you're trying to count the number of L that are before this AI. And there's, of course, exactly AI of them.
Okay, got it. Thanks.
Right. So, okay, now there's a pictorial way of seeing this as well. Now, imagine you order them to be weekly increasing. And then if you were to plot these in a histogram or something, so you would, or actually, let me make this decreasing because I think that might work better. So you first make this, let's say you put A1 cells, so 1 by A1 rectangle, followed by a 1 by A2 rectangle maybe, and so on. And so you get this shape, right? Some of you may recognize this uh, as a Ferrer diagram, but of course it's rotated in a weird way here. So you have this weird structure, and what you'll observe is that, okay, let's actually do this for particular example. So can anyone provide me with a sequence, a weakly decreasing sequence? Okay, we can, let's say we choose 5, 3, 3, 2. So in that case, what you do is you first draw this 1 by 5 rectangle. So that would look something like this. And then, of course, you have this again, and then finally you have this. So this would be your diagram sort of that you're drawing, right? And if you look at it, the sum of the AI is actually just the number of cells that this diagram has, right? So on the one hand, it's very clear what we're counting by the left-hand side. And now we would like to show that the right-hand side counts the exact same thing. So can anyone tell me why that is? So if you think about it, we're first summing by vertical rectangles, right? What happens if we try to sum by horizontal rectangles? Or if I were to ask you, at height x, what is the number of unit squares? Can anyone tell me that?
Bx.
It's exactly bx, right? Because that particular 1 by whatever rectangle would have exceeded that height x only if ai was at least x. And so you count exactly bx unit squares at height x. And so the sum of bx is actually just summing up the number of squares in this diagram as well, just in a different way. So here you were going by vertical rectangles, and here you're going by horizontal rectangles. Okay, so was that clear?
Yeah.
So very often drawing a two-dimensional table is also useful. Not here, but whenever you're interested in representing pairs, you can try plotting them in a nice little table and try to argue basically what it means for the conditions to be true with respect to that. Okay. The next problem is interesting. Let me attach. Right. So I hope all of you can see that. Let me explain. Maybe these words will be a little new to some of you. What this is basically saying is, we should specify that. Holds true and otherwise as well, but best to be safe. Okay. So, right. Yeah, go on. Athar and
Sorry,
okay.
there's some different.
Right. Okay. Yeah, I figured. Okay, so you have this alphabet of size scale. Let's say you have these characters, alpha 1 to alpha k. So for example, the English alphabet would consist of characters A, B, all the way to Z, and then you have 26 of them. And what you're being told is that you're given a set of words from W. A word is simply some letters from the alphabet. So you could have alpha 1, alpha 3, alpha k. That's a word, etc., etc. You have some words, there's no conditions on their length as such, but it's a finite set of words, right? And m of w denotes the length of the word, which is the number of characters that it has. And you're being told that there are no two words w1 and w2 that are part of w, such that w1 is a strict prefix of w2. What that means is the word w2 looks like w1 and then followed by some characters. So for example, ABC would be a prefix of ABCD, but it would not be a prefix of BCAD, for example. And given this condition, you want to prove this interesting inequality where you're summing over all the words in W and you're sort of assigning it a weight of some sorts, which is 1 by k to the length. And you want to show that this sum is at most 1. So of course, as usual, the hunt is for what object would you like to count, right? And so to do that, you would probably want to first understand how does one understand this condition, right? How do we model this condition in a reasonable way, right? Okay, does anyone have any ideas? Yes, that's good instinct. It indeed is sort of like a probability. Yeah, Athar, go on.
I think I got something. So like, um, we, I think we randomly choose, I'm not so sure to define it, but we randomly choose a string and like we find the expected number of values of the thing which is in W and like, yeah, so we take let's say the maximum length is n. We take a random string of length n, and in the random
Right.
string of length n, we see the we find the expected number of like things starting from alpha. No, so let's say the length n is the thing is alpha, yeah, alpha I, alpha j, on and on and on, and like we from each there are n possible substrings, so they're starting at 1 contiguous substrings. So we from those we see the expected number of them that lie in W. And now due to
Okay.
the containing thing, this is less than 1, but uh there are no two contain each other, but this can easily be checked to be the LHS.
Okay. Okay. Yes,
I think.
that is a solution. But of course, as you'll find that many times when you use something like the probabilistic method, essentially what you're doing at a very elementary level, or I should say at a very low level, is you're essentially just double counting. Under the magic of choosing things randomly, double counting. That doesn't this doesn't in fact take away from any, like, it's not supposed to oppose the power of the probabilistic method. Probabilistic method has its own uses because of course it made this, for example, very easy, and it would be in fact the recommended way of solving this problem as well. So we'll discuss both approaches and I'll try to explain how they are similar, right? Okay, so let's go over okay, how many people are familiar with expected value and things like that? If you are, you can raise your hands, for example, so I can get a quick count of how many people that is. Okay, that's not too many of you, but I think we can still sort of discuss that briefly. Okay. Okay, cool. So, right. Okay. So whenever you have a bunch of okay, so for those of you who know what tries are, this might seem familiar. And in fact, it is what that is what we're going to work with. We're going to work with a try. But let's start at the very beginning. So what we're going to do is we're going to build a tree. So let's do it this way. Let's say the root is the empty string, right? And now you have a bunch of children, one child for every character, alpha 1, alpha 2, all the way till alpha k, right? And the alpha 1th, or the child of the empty string, which for which the edge is labeled alpha 1, that is just the empty string appended with alpha 1, right? So for example, here you would have strings alpha 1, alpha 2 all the way till alpha k, right? And of course, this also has k children. So you build this infinite structure. But of course, we can sort of cut it at, say, level n if we want. We don't really have to continue with it forever. Okay, so, right. So this way you see that you have all the strings of length n as leaves of this tree, right? They're at the bottom layer, so to say, right? And there's going to be k to the n of them, right?
Yeah.
Okay. And so what that means is if you now were to take a look at the positioning of words in W on this tree, so they're going to be just vertices, right? And can anyone tell me what the special property of these vertices is? Okay, what does it mean for a word to be a prefix of another now?
Like they'll be on distinct vertices, having distinct values.
Right, okay. And but what encodes really the fact that it's a prefix of another?
It is on the
So
level
if I have a
above it.
okay, but you could also have, for example, okay, let's actually work with an example. Let's say the character sizes, sorry, the set of alphabets is 0 and 1. And now you are looking at all binary strings. So this is the empty string. This is, let's say, 0, this is 1, right? And this is going to have string 0 on it, and this is going to have string, let's say, 1, 0 on it. So obviously, 0 is not a prefix of 1, 0, but 0 is still at a higher level than 1, 0. So we would like something stronger, something that completely captures the entire meaning of what it means to be a prefix. A subgraph. I mean, subgraph is quite vague, I think.
Like an ancestor. Like the prefixes.
Yes, exactly, an ancestor. So for those of you who don't know what an ancestor is, don't worry, we won't need any of that. What you need to just look at is, think about
One
this.
second.
This
But
try is
when we say like it's a
essentially,
path, it lies on the path from the empty
yes.
word to itself.
Exactly. So the point is, what this structure or this try allows you to do is it allows you to talk about any string from the alphabet in a step-by-step process. So every string is not only a like every string is not only just a vertex. Every string can also be seen as a path. So if you have, for example, the string 0, 1 here, you start at the empty string and you look at the first character. You just start reading off those characters and you traverse those edges, right? And what you end up building is this path. So you have these paths, right? And what you're being told is that there is no two words such that W1 and W2 such that W1 is a prefix of W2. And what it means to be a prefix of W2 is if I were to start off at the empty string and go to W2 and add characters one by one, at some point I would see W1. That's what it means to be a prefix, right? And I'm being told that this never happens. So what that basically tells you is that there is no Wi and Wj such that Wi is an ancestor of Wj, or like I said, it lies on the path from the root to Wj, right?
Yeah.
Okay. So now let's try to look at this in context of this tree. Let's say the character size was 2. So in that case, you have this tree. I'm going to cut it here because I think it will become really messy if I draw more vertices. So okay. So how many vertices can you mark such that there's no two of them which have that property of being a prefix of the other? What's the maximum number of vertices, for example?
Eight.
8, right? Because you could just mark all of these leaves. But
Yeah.
But if you think about it, that's not a problem for the original problem, because what the original problem or rather that condition, what it very, well, I should say smartly captures is that it is easier to somehow mark things that are closer to the root. Sorry, it is harder to mark things that are closer to the root. and it's easier to mark things away from the root, right? It is able to capture that because it's like you're assigning this a weight of 1 because it has length 0. You're assigning this a weight of half, this a weight of 1/4 and 1/4 and so on, right? And so marking 8 of these at a level that is really low does not mean much. In fact, the sum total is in fact 1, which is still going to satisfy the condition given, right? So how do we capture this?
If we choose like some number from a higher level, then we can't choose any of the numbers below it. So we might just be able to generate equality.
Okay, I'm not quite sure I understood that. Could you repeat?
I'm working on like a rigorous proof, but it just like a few seconds.
Got it. Okay, so if no two satisfy this parent and ancestor relationship, that is, none of them lie on the path from this vertex to W2, the important property that you can show is that this is true in general as well for a general tree. So let's say this is the root, and you're looking at 2 vertices. So if you think about it, these sets are distinct, right? Like all the vertices that you could reach from this vertex.
Yeah.
Right? Or in fact, even more informally, what you could see this as is sort of trying to develop this procedure that preserves the sum of weights, but still makes it easier for you to do whatever you want to do. So imagine that. So this is a very step-by-step process. So imagine that some vertices are marked, right? And these are the things that are in W, right? Now, imagine you look at one of these vertices, right? And you look at its 2 children. This has weight, let's say 1/2 to the L. This is going to have weight 1/2 to the L plus 1, and this will also have weight 1/2 to the L plus 1, right? So now if I remove this from W and I add these 2 instead, the sum of weights stays preserved, right?
Yeah.
And is the condition also preserved? Is
Yes.
it possible that after this change, now I have 2 words, one of which is a prefix of the other?
It isn't.
It isn't,
No.
right? Because, yeah. It isn't because you have this vertex, this vertex, this vertex. So initially this was colored, which tells you that on this path, there are no marked vertices, right? Because otherwise you'd have a contradiction. And so otherwise you're looking at these 2 children. If you were to remove this and you put both of these here, then still there is no vertices on this path because of course now you remove that one marked vertex that you did have. And at the same time, you can't have any vertices that cause a contradiction from below, because if they did cause a contradiction from below because of this, they would be causing earlier as well. Right? And so sort of this process will preserve that condition for you. And you can keep repeating this, right? You can keep repeating this until you reach the bottommost level. Right?
Yes.
And the weight has stayed intact. And what is the weight of all the bottom leaves?
1.
That's 1. And so the total sum was 1 as well, right? And of course, now
Oh, yeah,
this
right.
entire idea can be rewritten in a double counting manner. So you can avoid doing things like this, which are, well, of course, complicated. And the way you do that is by looking at what essentially happened. If you had a vertex that was marked, and let's say we're working with k equal to 4, so you have 4 children at each vertex. What you do is essentially you send it, or rather distribute all of it along the leaves, right? Let's label these by their distance. The distance is precisely the length, right? The distance from the root is precisely the length of the word, right?
Yeah.
Okay, so let's say the distance is L. In that case, how many leaves will you end up with?
2 to the power L. Or
No. You have to factor in the total length as well. It'll actually be 2 to the n minus L, because all you're essentially doing is you have fixed the first L characters. So you have this string of length n. This is fixed because that's exactly this vertex. And these are allowed to vary, right? That's what it means. And so the total number of ways in a general setting is k to the n minus L. And since the total number of these leaves is k to the n, because there's k to the n length strings from the alphabet, that tells you that this sum is at most k to the n, and so most 1. And now you'll see the connection with why those arguments work, of choosing things randomly. What you're essentially doing is you're counting this. Let's say S is the set of all length n strings, right? So it's a set of all words that have n characters, right? So on the one hand, you have mod is equal to n to the k. And what you're counting is the number of pairs w comma w prime, such that w is a part of the word set that we had, w. W prime is a part of S, and W is a prefix of W, of W prime, right? So basically you have W and you have n minus length of W characters left, and you can fill them up in any way you want. And you're basically looking at the pairs of strings that satisfy this property. So if you count it by W prime, the crucial observation is that when you fix a W prime, that is a full n length string, at most one word can appear as a prefix, right? Because if you had 2 words that were appearing as prefix, let's say this was W1, W log W2 is the longer one, you'd have another one. And then the shorter prefix would be a prefix of the longer prefix, right? I think that might be the most number of times I've said prefix in a sentence. Okay, so you have this property that at most one prefix exists among all the n prefixes. And so on the one hand, for every W prime, you have at most one such pair, which tells you that there's at most n to the k such pairs. And on the other hand, if you were to count this, k to the n, that should be k to the n pairs. And on the other hand, if you fix W, there's k to the n minus length of W such pairs, because you can go over all those extensions. And so that tells you that this is less than or equal to k to the n. And of course, if you now divide out by k to the n, you will get precisely that result. And this is very similar in spirit to the expected value idea. Not so much expected value, but something like that. And the point is you're just generating a random string of length n with characters in alpha 1 to alpha k. And you're looking at the event, some word of W is a prefix of my string. That is the event, right? And you're trying to estimate the probability of this event. Now, probabilities are always at most 1. So on the one hand, you have at most 1 on one side. And next, the crucial observation is that if you have 2 words W1 and W2, which are both part of W, then the events that W1 is a prefix of your randomly generated string, and W2 is also a prefix of the same string. These two events cannot happen together, right?
Yes.
Which tells you that the probability that at least one of them happens is simply an addition of all of those probabilities. And the probability that it matches with the first n strings of that is like, okay, so if you have some word W and you're trying to see if a length n string has that as a prefix, the prefix is already fixed, right? It's the first W characters. And the other characters you don't even care about, because no matter what they're generated as, my job of checking whether it's a prefix or not is done within the first length of W characters. And the probability that it matches 1 by 1 is 1 by k. And because there's m of W characters, the total probability is this. And so when you sum this up over all the words, you get the total probability of this event, which has to be at most 1 because it's a probability. So expected value, of course, is a little overkill here. You don't need that. But yeah, this is the random idea. And you'll find that, of course, these are essentially the same thing, right? So the probability idea, if you were to, sort of convert that into the double counting idea, it would basically become counting the pairs of strings, W and W prime, such that one is a prefix of the other. Okay, any questions? Okay. One thing I should mention is that you can actually prove this very interesting result known as the Lubell. Yeah, I hope I'm remembering this correctly. Yes, this inequality, which essentially states that if you have a set S of size n and you pick some subsets A1 till AM from S such that no AI is a subset of another AJ, right? Then so you'll find that families of these sets, they're called anti-chains. So I is part of M, and of course 1 by n choose AI is at most 1. And the proof runs exactly the same as what we've discussed before, but of course you have to tweak it a little because these are subsets and not strings anymore. And the same probability argument will also work. And of course, there's a double counting way to do this as well. Okay, okay, yeah. I think if there are no questions, we can move on to the next one.
I'm sorry, but how do you just do the expected value argument?
The expected value argument is essentially, you look at this event 1W is defined as this random variable means, okay, let's say the randomly generated word is S, right? And then 1W is just 1 if W is prefix of S and 0 otherwise, right? And what you do is you estimate this.
Okay.
And if you look at it, this expression is just the left-hand side on the one hand. And on the other hand, it's at most 1 because you can't have two words both being prefixes.
Okay.
So of course, here you have to use linearity of expectation, which is actually not required here because these events are independent. They don't even happen together. And so, sorry, not independent. These events don't happen together. Yeah. Okay, right. So the next is a bit of, okay. So next, I think, of course, graph theory is one place where double counting is very useful, especially when you're, of course, because in double counting, because in graph theory, you will count many times pairs of objects and all. I think a very instructive example, which is sort of a blow up of the classical, a graph avoids a cycle of length 4 idea. So, okay, let's say you have, let me touch this statement. Right. Okay. So you have this graph G on n vertices such that it doesn't have the complete bipartite subgraph, or sorry, the complete bipartite graph with partite sets having size k as a subgraph. And so you have to show that the average degree of G is, okay, this notation, if it's a little confusing, let me just explain what it means. So assume K to be fixed, and then you just have to show there's a constant C such that the average degree is at most C times n to the 1 minus 1. In particular, when K is equal to 2, K 2 comma 2 is just a cycle of length 4. And there you have the normal result that if G avoids a cycle of length 4, then the number of edges that G could have is n to the 3 by 2, or that order. Okay. Right. Okay, so does anyone have any ideas? What should be the object we double count? Right? A K by K simply looks like this because it's the complete bipartite graph. Will sort of look like this. Yeah, something like that. Can you explain the notation again? Okay, so no need to get worried by this. You just have to show that the average degree of G, there exists an absolute constant C, which is allowed to depend on K because K is fixed. K is fixed. So you can imagine K as something fixed, such that and you have to show that the average degree of G is at most C times n to the 1 minus 1 over K.
So Cn can be a function of K.
Uh, n of course is different, but C can be a function of K, yes, because K is fixed, but C has to be absolute. It can't depend on n, for example. It can depend on K. Okay, so if you had to find K, comma K, how would you do it? What are some possible strategies? So let's say I give you a graph and I ask you, is there a K, comma K in this? How would you go about finding it?
Looking at the number of odd cycles or like that.
The number of odd cycles. Well, not quite. Odd cycles will, like, in fact, not be useful because
Coloring
K,
it,
comma K
probably.
doesn't have any of them.
Coloring it, maybe we can try.
Coloring it, okay. So coloring it in, like, let's say some colors, like chi of G colors, let's say, a chromatic number. How would that help us?
So there are like K points of one color and K points of the other. I think we will have a bipartite graph in K.
No, not quite, because the chromatic number is again something you don't have any control over, right? And the coloring could look very weird. And okay, so if you had to again like look for a k comma k, what would you do? One dumb strategy is to just test all 2k vertices, right? Or actually rather instead go over a set of k vertices and another set of k vertices and just check if all k square of those edges are actually there, right?
Yes.
That is one very dumb strategy, right? Another strategy could be to instead fix a set of k vertices and locate any vertex v that connects to all of these. And if there's at least k of these, then you have a k comma k, right?
So k comma k means like completely bipartite?
Yeah, the complete bipartite graph. So this, of course, this is k comma k.
Okay.
Okay, so let's say we fix a certain vertex u, or rather, sorry, let's say we fix a certain set of vertices u1, u2, all the way till uk, right? And let's say you try to count the number of vertices v such that v is connected to all of them. How many such structures do we have of vertices v and a set of k vertices satisfying this?
Less than k.
Sorry?
Less than k.
Less than k if you fixed this, yes. But what if these are allowed to vary as well? What happens then?
Less than 2k?
Why? Where does 2k come from? Okay, how many ways are there to select this set of vertices u1 to uk?
NCK.
N choose k, right? Exactly. And for each of these, you have at most k minus 1 such vertices. So on the one hand, you have at most these many such structures. What I mean by structure is a vertex v and a set s of size k such that modest is k, size cardinality of s is k, and v u exists edge uv in g for all u in s. So v is connected to everybody in s. You're just counting the number of pairs of vertex from a set. And on the one hand, you have at most k minus 1 times n choose k of these. But how many of these do you have by counting by v, let's say? So if I have a given vertex v connects to some people, right? Let's say it will connect to a degree of v people, right? So how many of these satisfy the requirement?
DVCK?
dv choose k, exactly. And so here you have this sum. Does everyone agree till now?
Yeah.
1 second. How do you get the right hand side bound?
The right hand side bound is by fixing this set S. So you're counting these pairs. One is by V and one is by S. when you count by s and when you fixed these, if you have up to k vertices that satisfy this condition, then at that point you've already found yourself your kk, which can't happen because the graph is supposed to avoid this.
Okay, fine.
Okay, and of course, this is another very common thing you'll find in double counting problems, especially in graph theory when you have sums like this. Here you can use Jensen, right? Because x choose k as a function is convex on the interval you're interested in. And so this is going to be at least the average degree times n, right? Does everyone follow? And so we have this. Now, because k is fixed, this is of the order n to the k, this is of the order d to the k, and this is just k, so you can also ignore this. So this in terms of orders is bigger, and so n of course here as well, and so you get n k minus 1 by k is bigger than the average degree, and this is of course k, and so you get that there is some absolute constant c such that the average degree is at most c times n to the 1 minus 1 over k.
So how do you apply Jensen?
We applied Jensen here, right? We used Jensen when we said that this is at least n times the average degree. Sorry, not sum. Right here.
Okay, then
And then, of course, the bound follows because you get this inequality, and then this is less than k times n to the k. This is bigger than n times k by k factorial, let's say. And if you unpack all of that using these two, you will get that there is some constant c which depends on k, such that the average degree is at most c times n to the 1 minus 1 over k. Okay. So this general theme shows up in many places, and we're going to discuss an example of it, which actually shows up in a very a seemingly unrelated setup, and that is geometry. Okay, so right. Okay. Okay. Yeah. So the problem basically says that you have these endpoints marked in the plane, and you're looking at these pairs that are at a distance of exactly 1. So for example, you would not mark either of these, but maybe this is also exactly 1. And you want to show that the number of such pairs can't be too big. So it's like at most 10 root n times some constant c.
So we have to find the constant or prove the existence of the constant.
Prove the existence of a constant. So you could present an absolute constant c, or you could prove that there is a constant c. Of course, we're going to find an absolute constant c, but it doesn't really matter too much because, yeah. How many of you know about Turan's theorem? It's not required here, but just to get a general sense. I see. Okay, so given 2 points P and Q, how many points R can you have such that RP is RQ is 1? Or in a very graph theoretic way, how many common neighbors can 2 vertices have?
2.
Is there an upper bound on this?
2, I think.
2. Okay, why is that?
Because if you draw circles of radius 1 and on centered at P and Q respectively, there are only like 2 intersection points.
Perfect. So if you draw a circle centered at P with radius 1 and a circle centered at Q with radius 1, then it intersects in at most 2 points. And so P and Q, any 2 points in the plane, can have at most 2 neighbors. Right? Okay. So what that tells you is that you can't have this. Which is a K2, 3. And so our aim will be to adapt the previous proof and make it work here as well.
So we're just converting the geometry like stuff into a graph.
Yes. Yes, that's right. Which parts specifically? So what we're doing is we're building a graph G on the n vertices, where you have an edge PQ if and only if P and Q are exactly 1 apart, a unit distance apart, right? And then they were observing that this graph avoids a K2, 3. Why that cannot be more than 2 points? Okay, so if P is neighbors with some point R, then that tells me if I draw the circle centered at P with radius 1, then all of those points, all of its neighbors must lie on this, right? And so if I look at a vertex Q, and draw its circle, these intersect in at most 2 points. And so P and Q have at most 2 common neighbors. It could touch, but it would never have 3 intersections. Yeah. Okay, so I think I'll give a hint because I think that might make it a little more approachable. So we're going to count triples of points. Well, actually not triples, but this is using for now. So triples of points P, Q, R from the set S such that PQ is 1 and PR is 1. Both of these should be true. So really you should think about this as this set Q, R, very similar to what we were doing earlier, right? You fix a vertex V and a set S as that V is connected to everything in S. Here it's just the set S has size 2. So if we count this by P, can anyone tell me how many pairs I will have? Let's say I have a point P and it's connected to degree of P people. So all of these are at distance of 1. So it's like you have P, the circle, and you have
So DP choose 2, I think.
DP choose 2, exactly. And this is going to get summed over all the points. So you have exactly these many pairs, first of all, right?
Yes.
Okay. The second thing we would like to determine is an upper bound on this, or instead counted by Q, R. So how many ways are there to choose Q, R?
So twice into NC2. Because there are two
N
options
choose
for
2
each choice.
first, yes. And then there's up to 2 P that could work. You can't have 3 P that work, right?
Up to 2.
And so you get this. And
Yes.
now, as we discussed before already, by Jensen, this is at least the average degree. Choose 2 times N, right? And so that just tells you this, which if you cancel things off, you will get something like this. And that will tell you that D is less than 1 plus something like root 2 times root 2n, right? So the average degree is less than 1 plus square root of 2n. And the number of edges is equal to sum of all the degrees divided by 2,
By 2.
which is equal to dn by 2. And because d is less than something like root n, 2 root n, let's say. And so dn by 2 is less than n to the 3 by 2, just by multiplying by n by 2. And so in fact, c equal to 1 works, but I don't think it works always. It works for large enough n. So you can probably make c something like 10 and it will always work. Okay, any questions?
We just like found scenes, no need to like, we didn't prove the existence like in the previous.
Yeah, in the last one, we didn't prove the existence of C. I mean, we did prove the existence of C, we just didn't compute what it was precisely. Here we can say some, like we can easily say that, okay, equal to 10 works. You can't make that explicit there because it's a weird function of K and it requires optimizations that I did not really want to discuss because they're not the main point of double counting anyway.
Okay.
Okay.
So like we
So
just
of course, now, yeah, go
sorry,
on.
but we just replaced K with 2 here, right? In the pre like the
Yes,
K in
yes,
the
that's right. Yeah. So in fact, this will work for any. So in general, this should give you an idea of what it's like if in general k m comma n is being avoided. If m is equal to n, in that case, you're happy anyway because you have some bound from what we already discussed. On the other hand, if m is less than n, then what do I do? Right? Because there are two possibilities now, right? One possibility is I fix a vertex v and a set s of size equal to n, right? And then I see how many people are connected to all of these, right? And this is going to be less than m, something like that. Or I could switch it around and I could choose this. And what we just discussed should give you an idea of which one belongs here. So you should choose the one that is smaller as the one whose set you create. Because in this previous one, here we know that there is no k2 comma 3, right? Which means that there's also no k3 comma 3. So we could have then used our previous result and gotten something like c times n to the 1 minus 1 by 3, which is equal to cn 5 by 3. This is worse than cn to the 3 by 2 because 5 by 3 is bigger than 3 by 2. Sorry. What have I done? Okay. This is the number of edges, right? So here we need to look at average degrees. So it's a little different. So here the average degree is cn to the 2 by 3, whereas there you're only guaranteeing n to the 1 by 2. Okay. So let's end this with an IMO P3 now. It's quite old, Arvind, but it's fine. Okay. The setup is going to be a little similar to what we've already seen. So hopefully this will not be too difficult. Okay. So I hope all of you can see the problem. So this is from 1988 or something. Okay. So the problem says that you have some points S, and you're given that no 3 points in S are collinear. So this doesn't happen. And at the same time, for every point P that you choose, there's at least K points that lie on a circle centered at P. Of course, this distance is not in your control. There is just some circle centered at P which contains at least K points of S. And then you want to show that K is something like of order root n.
So we could try the distances between the points.
What do you mean distances between?
So if, let's say, Q and R are equidistant from P,
Right.
distance D, say, or something,
Okay.
then QR is less than 2D.
Okay. Yes, that is correct. How does that help us?
Haven't really thought of that, but
this is a good idea to look at isosceles triangles. Because there's going to be a lot of them, right? If you have P and then if something like these many triangles, all of which are isosceles, that's a lot of isosceles triangles that P is a part of, right? So let's look at that. Let's take a look at all pairs A from S and B and C also from S, all distinct, such that AB equal to AC, right? So how many points like this could we have? So let's count this object, right? So if I count by A, let's say, can anyone tell me a lower bound on this? So I'm counting by A. This is,
greater
let's say,
than
the
equal
number
to
of
k
these
choose
pairs
2.
is let's say n, right? So if I fix A, it's at least k choose 2 because there's k points which are equidistant on some circle centered at P. So you have some circle centered at P, and then you have k points marked here, and of course all k choose 2 pairs will fit as B comma C. And so for every A, you have at least k choose 2 of these, right? Now because S is n, that tells you that n times k choose 2 is less than or equal to n. What about an upper bound? If you count it by B comma C, how many pairs might you have then? Sorry, how many pair of vertex comma set, something like that. Yeah.
N minus 2.
Yes. Okay. Fine. That is fine. So you have to n minus 2 times n choose 2 things.
N
But you
choose.
see the problem with this. The problem with this is that n choose 2 and n minus 2. Okay. So n minus 2 is basically of order n, right? That's at least that's as large as n. That's
Yeah.
not going to be much smaller. And so these two expressions are not so useful. And so you could sort of just cancel them off because they're roughly of the same growth or same order, not growth. And so you have k choose 2 at most n choose 2 roughly, right? And that just tells you that k is at best linear in n, right?
Not that useful.
No, not that useful because you already knew that. Of course, you can't have k bigger than n because k is the number of points in S. No, so if you have some 2 points B comma C, how many points can you have that are equidistant from both of these?
Oh wait, 2 only, right? Because it's they can't no 3 can be
Yes.
collinear.
Yes, exactly.
And they all
So
lie
because
on
no
the
3
perpendicular
points
line.
are, yes, exactly. So any point A that satisfies this must lie on this line. And you've already been told that no 3 points of S are collinear, right? And so at most 2 points will satisfy this property. And so you have 2 times n choose 2 here. And this is pretty good because now 2 is quite small compared to n, right? So in terms of the rate at which this function grows, we're fine because this is roughly n squared, let's say. And this is n times k squared, right? And so if you cancel off those n's, you get k is roughly root n, which is what you want. Now let's just make the bounding precise because this problem asks for a precise bound and not just NEC. So here, if we just start unpacking this, here this is n times n minus 1, right? And here you can just cancel off the n. So you just get k times k minus 1 is at most 2n minus 2, right? So k minus half whole squared is at most 2n minus 7 by 4, right? By adding 1 by 4 to both sides. And so you get k is less than or equal to square root of 2n minus 7 by 4 plus half, right? And because this is strictly less than square root 2n, we get this result.
So we actually got a tighter bound than the question asked.
I wouldn't call it tighter because 7 by 4 is quite small, right? So if you take n to be something like 1000, there is practically no difference between the two bounds. So I think
Okay.
the problem is pretty much tight as it is. Tight in the sense that the bounding we got is closely matching with the requested bound. It's interesting to think about the other direction. Can you actually construct sets such that K is large? So can you have points like that? Okay. Right. So I think it's close to 7:30. I think we can stop here. So yeah. After looking at this problem, how would you identify this as a double counting problem? Okay, that's a good question. That's a good question. So we can go into some more meta things like that. So imagine you have something like this. Now, so for every point P, you're being told that there's at least K vertices, K points, sorry, that are equidistant from P, right? Now, because it does not really matter what distance they're at, all you're being told is there's at least K of them, you might as well draw those circles, right? So you can draw this circle, and now you have at least K points lying on this. Now, this vertex will also have one of its own circles and so on, right? So that's the first observation. And then the idea is that because this is true, some 2 points cannot lie on too many circles together, right? And yet, if K is greater than root 2n, then for every point P, you're able to produce at least of order n points, or rather n pairs, sorry. You're able to produce n pairs that lie on a circle together, right? That lie on one of these circles. And if you go over all the n points, this is giving you at least n squared pairs. And that's too many pairs, because any given pair of points can have only at most 2 circles it's a part of. Because if it's a part of 3 circles, then those 3 circles are of course coaxial, and so their centers will be collinear. But that can't happen because no 3 points of S are collinear.